Hello, and welcome to our presentation on machine learning for finance and trading. This presentation is by Adam, Kat, Effie, Alana, and Danny. Our financial problem is we cannot predict market behavior. It's influenced by more than just numbers. It's influenced by public sentiment, news, politics, and many more external factors that play a major role in the market fluctuation. All these factors make the market volatile, and market volatility prediction is a primary way of managing risk and making informed investment decisions. Volatility refers to a degree of fluctuation in the price of an asset security or just the overall market behavior. High volatility is when prices swing up and down rapidly, while low volatility is when the prices remain stable in the market. Machine learning offers a powerful tool to navigate these complexities and uncover patterns in market volatility. This study explores modern ML models, XGBoost, Random Forest, and RNN against the classic GARCH model to find which is the most effective.
For our models, we drew from three different data sources: Hacker News, Reddit, and Yahoo Finance. We used BigQuery to pull 3 years worth of business and finance article titles, URLs, and comment metadata from Hacker News. Some limitations that we found while acquiring this data set included the fact that Google Cloud billing is required, as well as there being data quota caps and occasional missing fields. We use the Python Reddit API wrapper, or PRA, to fetch real time comment data from subreddits like Wall Street Bets, stocks, investing, quant, cryptocurrency, ETFs, and real estate. We encountered several obstacles while fetching the Reddit data, like the shutting down of Reddit's push shift, which made it more difficult for us to obtain the data. PRA having rate limits, there being Tigger false positives, and only having access to the top 1,000 posts. Despite these obstacles, however, we were able to collect roughly 1.2 million posts and comments over 1 year from over 40 finance related subreddits. Our third and final source was Yahoo Finance, or Y Finance, which provided us with historical returns and volume data project, and we were able to obtain 3 years worth of stock prices, volume, and volatility data. Due to Reddit's limitation of only allowing 1 year's worth of data to be downloaded, we decided to split our raw data into two datasets for modeling. The model that used only 1 year's worth of data referenced all three of our data sources, meaning BigQuery, PRA, and Y Finance, using data from the time period of February 2024 to April 2025. The model that used the 3 years worth of data only referenced our BigQuery and Y Finance data sources, since we couldn't get 3 years worth of Reddit data, using data from the time period of January 2022 to April 2025 index. We ultimately ended up only including tickers for which there were comment data for more than 70% of the days. And this resulted in 15 total tickers for the 1 year data, which was actually preferable, since having too many features over only a year long time period would quickly result in extra noise being added to the model. And for the 3 year data, a total of 28 tickers were selected, 22. The 1 year model dataset contains data for 4,892 days across its 15 tickers and has 7 features. The 3 year model dataset contains data for 21,978 days across its 28 tickers and has 3 features, which it shares with the 1 year model. The target for both the 1 year and 3 year model datasets is the next day realized volatility. In this table provided, we have listed the features that our model uses as well as their descriptions. We dedicated a lot of our time to thoroughly cleaning the data, remedying issues like size differences, ticker misrepresentation, and web scraping limits. We ensured time alignment by re-indexing all of our time series to NYSE trading days, making sure to account for weekends and holidays. We were able to identify holiday dates because every ticker was missing the same number of days in the finance data, which we have shown in this output code snippet below. We addressed missing data by filling missing sentiment or volume with a zero, assuming neutral sentiment, and dropping rows with NANs after lag features were created. This other output code snippet below shows our checking in success in removing all of the NANs from our data. Our other pre-processing steps included cleaning the raw data by removing HTMLs and putting everything into lowercase, applying Vader to perform sentiment analysis, and matching tickers using keyword heuristics. We also aggregated sentiment and volume per ticker per day, aligned them with stock volatility metrics, and scaled features to avoid magnitude dominance. However, despite our thorough pre-processing, our data still has limitations. For example, social data has noise like sarcasm, spam, and irrelevant content that we couldn't accommodate for, which may have distorted our sentiment with mismatches or false positives. There may also be a time lag between news and social posts and price movement, which our lag features only partially address. A bias that our data is susceptible to is platform bias. Hacker News and Reddit likely have demographic and topic biases that skew towards tech and retail investor interests, which could skew sentiment and volume patterns towards certain tickers. Additionally, our analysis ultimately excludes stocks that have no comment or sentiment data, meaning that they were not discussed on social platforms, which introduces the possibility of survivorship bias in the data. This means that our findings may not be able to be generalized to stocks that are less mentioned, less volatile, or less known.
Our baseline method is the GARCH model. This serves as a traditional price-based benchmark against ML models using text features. Our input is previous 3 days of conditional variance and squared returns. Our GARCH model then produces conditional variance for the next day, and we take the square root of this to get the standard deviation, which is what defines volatility. And then we compare this to our target values, which are the next day volatility pulled from our Y Finance dataset. Trained with a walk-forward rolling window of the past 3 days, one model per stock per day, using only historical data to avoid leakage. Instances with insufficient history are logged and are skipped. Our GARCH performance measured as follows. You can see in this graph that we plotted true volatility against our GARCH model predictions. We used the root mean squared error in order to value what the error difference is between true and predicted volatility. We found this to be 0.0115 across all tickers, and our goal is to improve this error using different machine learning models.
Now I'll talk about our use of XGBoost, one of the machine learning models we use to predict next day stock volatility. So first, what is XGBoost? Extreme gradient boosting, or XGBoost, builds a series of decision trees where each new tree learns from the errors of the previous ones. This process is known as gradient boosting, and it allows the model to correct itself over time and converge towards a more accurate prediction. So why did we pick this model? First, it is designed for structured data and especially time sequential data sets. It also has built-in regularization to reduce overfitting. Plus, it scales well for large data sets and is ideal for mixed features, like in our case, we have finance and sentiment-based features. When building our model for XGBoost, we wanted to try multiple methods across both the 1-year and 3-year dataset. We decided to do walk-forward testing in a time-aware 80-20 test train split. These models were trained per ticker such that they were not trained on the full dataset. We did this to prevent data leakage and allow learning of stock-specific volatility patterns. We also ensured reproducibility by fixing a seed. Now we can see that our 3-year model using walk-forward testing performed the best, so that is the model we chose to represent for XGBoost. And in this model, we used the 3-year dataset features previously discussed. So as we saw before, our primary metric was root mean squared error, or RMSE, with it having an average RMSE across all tickers of about 0.0068. In the graph, we see the predicted versus target volatility for the ticker AAPL, which is Apple. We see that predicted volatility closely follows the actual trends. However, it is less accurate on extreme highs and lows. Now we can see how XGBoost compared to our baseline GARCH model. We see that it did perform better than the baseline, which suggests new sentiment improves prediction accuracy. We also note that it seems like GARCH tends to underestimate volatility, which we will further see on the next slide. So for our error analysis, we looked at residual analysis, where we compared prediction errors of XGBoost and GARCH. So we see the histogram of residuals, And as said before, we see that GARCH model tends to underestimate volatility. And on the other hand, we see XGBoost has a more balanced error distribution. So now we have some final remarks. One major limitation is that it does not inherently model the dependencies, the time dependencies, and is more dependent on good feature engineering, which is why we included lag features. But for our key takeaways, as we saw, our XGBoost model showed that combining traditional market data with alternative data structures like sentiment can improve volatility prediction. While not perfect, it did outperform the traditional GARCH baseline.
Model because we found that it reduces variance because it's built off multiple classification and regression trees, and it takes their averages, and it handles overfitting well. Furthermore, we thought it was easy for prediction because we were able to classify our prediction target into a binary output, and thus it would be easy to integrate into trading strategy. And finally, we chose our prediction threshold for this model to be the top 30% of high volatility days. It would be the number one in a predicted time period or zero otherwise. And you can see a model roadmap on the right. So for our main evaluation metrics and findings, we found that the F1 score of the positive class was going to be our best metric because we were flagging on such a strict threshold, for which you can see the equation in the bottom left here. And we also wanted to test for the ROC AUC, or the rate of change area under curve, because our prediction threshold was so strict, and that metric actually gives us an average of the model's performance regardless of a prediction threshold. And finally, we found that our F1 score for this model, considering sentiment in Yahoo Finance data, was at 0.75, and that the accuracy was 0.85, so it performed relatively well. We found that the realized volatility feature dominates as well, and that the sentiment data was very low in its signal strength, but it still had a signal strength. Finally, we see that our average F1 test score and train score stagnates at about 3 tree depth, so that kind of shows that the model is lacking in complexity. So next, grids, and we found the optimal depth via grid search and stratified k-fold cross validation. So next, we compared our random forest model to our baseline GARCH model, and we had three models here, as you can see in the graph, comparing their F1 and their ROC AUC. We classified the GARCH predictions obviously into a binary target by the 70th percentile threshold, and for our base random forest, which would be defined as just Yahoo Finance data, we had a metric as well, just to see if sentiment was actually improving the model at all. And you can see the RF base plus sentiment actually performed the best in terms of AUC and average F1 among all the three models. And notably, Random Forest performed far better than the GARCH model overall. And you can see that we wanted to test to see if that improvement on sentiment was noise or not, so we carried out cross validation with 5 folds, and it actually confirmed that the sentiment features with the Yahoo Finance features added about 0.01 accuracy to the F1 and ROC AUC values. Next, we wanted to do walk forward testing, and we conducted that, and we found that there was a high ROC AUC rate of change compared to accuracy almost at all points, which showed that there's severe class imbalance or overfitting likely occurring, and accuracy varies widely over time, showing that it's very representative of market sentiment at that time, which is to be expected for the stock market. And this led us to the proposal that we need to use AUC ROC for future model comparison, because the 0.7 threshold that we chose was too high for the model to fit on. Next, we carried out one hot encoding on the stock tickers because we knew that we had hit a information threshold because our tree depth was so low, and we added one hot encoding on our stock tickers, and we found that the cross-validated AUC and F1 scores actually improved the models by about 0.01 compared to when they were just the sentiment and base features. And we manually tuned the tree depth by plotting the train and test error, and there you can see here that kind of reduced overfitting. And then you can also see that in terms of feature importance, tickers like Tesla and Nvidia were now second and third, showing that there's likely an imbalance in our data's comment volume. Finally, for trading strategy and limitations, obviously we need more data for this 1 year model, or dynamic imputation rather than just converting nans to zero. Maybe like a rolling average would be better. Model also struggled to identify positive and negative cases correctly due to a strict threshold, 0.74 F1 score, as can be seen in the trading strategy we employed here, where about 367 of the 123 samples flagged a 1, meaning it would be a high volatility day. And here are some of the examples of that. So maybe some next steps would be to use more lags or sequential data like an RNN to increase the sentiment signal strength, or utilize dynamic thresholding for different features. Thank you.
Hi, my name's Adam Mazzoudi, and I will be going over the recurrent neural network LSTM long short-term memory model for our volatility forecasting. So why did we pick LSTM? Well, there's a few reasons why. It's best at capturing some temporal patterns in our sequential data. It's really important that we use this because we have such a big time frame, 3 years, and we have to find certain patterns and be able to store memory essentially, and some hidden cases there that we can keep over time and learn from. So it incorporates lags and its smooth features to reduce noise and overfitting. That's something that this model is going to be best at. And we see that because it already outperformed the baseline and XGBoost in its predictive accuracy. And what we have on the right is just a table of sort of an index of the next few slides. And at the bottom here is a 3-year true versus predictive volatility sort of comparison timeline scatter plot thing. And yeah, so that's just for sentiment volatility over time. So for our features and parameters, we have a few things here, but I'm really just want to go over the important features. We have realized 3-day volatility. So this is just sort of an aggregated 3-day rolling realized volatility that was pre-calculated from our sentiment over time that we got from Reddit. Or I'm sorry, not Reddit. Reddit and the news. We have a combined sentiment lag, so just 1-day lag sentiment for Reddit and news. Same thing for combine the volume. We have a binary flag for any missing sentiment. So for days, since it's such a huge time frame, we need certain days. We know there's going to be certain days where we're just not going to have anything, and that's definitely true. That we see that here happening, and we need to be able to flag that and be able to work around that in the model training. So here we engineered some of the features. The target smooth. It's a smoothened version of the next day volatility, and this uses a 3-day moving average as well. So some good features about this include the 80-20 train test split, the fact that it's time aware. We actually incorporate 3 layers in this LSTM. So, and I'll talk about that in a second. We have some more creative features that we spoke about earlier, the lagged ones, and that was just created by shift functions and pandas, and the code is pretty self-explanatory, so I don't want to spend too much time going over details there. So some more things that are important are the loss function and the optimization of this model. So it's really important that we have a good optimizer working here, and we chose Atom for that. For our loss function, MSE loss just emphasizes the large errors that we dealt with. We trained the model for over 300 fixed epochs, so we didn't do any early stopping, and that was just for convenience sake. Our dropout rate was 0.3, and that was just to prevent overfitting. And obviously this took about 15 minutes of training every iteration, so it was important that we fine-tune this so we don't waste too much time. So the architecture and the inputs, so like I said, we have 3 layers, each with 128 hidden units. We have 10 consecutive days as our sequence length, and our final output is generated through a hidden layer. So our first layer kind of acts as a low-level pattern detector, so it just takes in the raw features and the learning trends. An example would be like, higher sentiment yesterday would be low volatility today, and it acts like kind of like a feature extractor over those 10 consecutive days. The second layer would be the sort of like the temporal or like seasonal pattern refiner. So it takes the output from our first layer and it just continues over time and it learns the interactions over long windows, so longer and longer windows. So that's like where our epochs come in, without overfitting. The third layer is sort of like the reasoning of everything. It's kind of like that's the time aware aspect. So it's the decision making, like reasoning layer. So all this kind of comes together in a beautiful way, and we see some pretty good outputs here that I'll show you. Um, so here to the left is a scatter plot with our true volatility over predicted volatility of our LSTM. And these are just some of our results. So we have our R squared score, so 78.35%, which is really good for something like, Reddit news sentiment. Like, I think this is one of the better models. This one, and I believe the Transformers did pretty well. So yeah, there's the mean average percent error. There's directional accuracy and mean average error as well. So yeah, so high correlation, as we can see, very strong data, very highly correlated, and the model just did a great job. And as we can see at the bottom right here, so some permutation feature importance is what it's titled as. We see the most important features that were used to make these predictions. So some comparisons between our RNN and the base model, as you can see here, definitely fit better. No underfitting, as you can see. I mean, it was pretty linear. It did a great job, way better. Our MAPE comparison and RMSE comparisons as well just show that face on, so I don't think I have to spend much time going over that. The last thing I wanted to speak on was our project executable, so the architecture. So this is going to be sort of something I'm going to bring up towards the end of it, but I'm going to go ahead and send an email to the professor and talk more in detail about this, just because I want to save some time in this recording. So
Our conclusions found that LSTM and XGBoost outperformed the GArch baseline in predicting next day volatility. Random Forest also benefited from sentiment data improving F1 and ROC AUC scores. Though sentiment and volume data were not top features, they improved the model's accuracy, and machine learning models generalized better than traditional methods. But they still all underestimated extreme spikes, probably because market volatility is a very difficult thing to estimate. Random Forest performed best on 1 year data, and we predict this is due to its sensitivity to feature richness over sample size. XGBoost and LSTM perform better on the 3 year data, possibly because XGBoost adaptively weights features based on their importance through gradient boosting, and LSTM captures time series dependencies well through its neural networks. What did we learn? Well, we learned sentiment data can improve next day volatility predictions, but is noisy and needs careful pre-processing. We learned how to model a time series data and avoid data leakages, as avoiding look-ahead bias is vital to training an accurate financial model. Model success depends on thoughtful feature engineering and robust validation, and even a slight improvement in model accuracy is a huge win in the financial world. Creating a clean and usable raw dataset is more time-consuming than we thought and vital to creating an unbiased and helpful model. So in the future, we could run further analysis to investigate why random forest perform better on the 1 year dataset and why XGBoost and LSTM outperform random forest. As right now we have a prediction, but we don't have concrete proof to back up this. This would then guide the development of an even more improved model. We would also use intraday data. So right now we're using daily returns, but intraday data could reveal volatility spikes or microstructure patterns that daily data smooths over. Rather than manually labeling financial news or tweets, we could leverage domain-specific LLMs like FinLlama to extract sentiment, even for niche or emerging topics, without training a new model. This is especially useful in fast-moving markets where labeled data doesn't exist yet. Order flow tells us how aggressively people are buying or selling, and options data gives insight into hedging pressure and risk expectations. These could give us a more nuanced view of what true volatility drivers are. Once we have a model we trust, the real test is whether it adds value in a trading context. So we would backtest in a realistic market condition to see if it actually helps make better decisions or if these are just hypothetical predictions that don't work in reality. Thank you for listening to our presentation.